Perfect. Just give me a moment. Just give me a moment. I can start the record. Yeah. So thanks, Canvi, and thanks everyone for hanging out till like the third session. And so today it will be like a bit mathematical, not like very mathematical, and we will be only try to discuss things at, I would say, at high enough level, so that we can use the ideas from topology for quantum error correction. And in particular, I will discuss homology and co-homology, and what are these terms, their meaning and all, become clear, as we speak. And yeah, so so let's see, what it is. I mean, and these techniques are super useful, not only in quantum error correction, but in different areas of quantum information. So I mean, it's good to know these tools as such also. Yeah. Okay, perfect. So let's look at what we covered so far. So we had session on classical error correction, basics of quantum error correction, and the stabilizer formalism. And then we had a session on Tori code on March 14. And today we are going to talk about introduction to topology. These are the references, and you can see the link to the videos and slides in the chat, and also you can find there the website link, and you can access it. All the relevant resources from there. And people who will be watching it later, I mean, yeah, you can just access everything will be posted on the website. So it's everything is contained there. So this is the overview. So we will discuss what happened last week. Then I will give some motivating examples, why you should be interested in topology. Then some basic topology, and the notion of homology, then co-homology, and summary. And I will be talking about in particular, Z2 homology and co-homology. And the reason is that we will be interested in qubits. So if you are interested in qubits, you can look at ZD homology and co-homology, which is a generalization of Z2 homology and co-homology. But I mean, it's a bit involved, so we will not be talking here. But let's say in future, if we have a follow-up, part 2 of this course or something, we can discuss there. But for the moment, I mean, I think in this tutorial, we will only focusing on Z2 homology and co-homology. Nice. So yeah, so I mean, as I mentioned, the Z2 homology will be important if you want to develop quantum error correction codes for qubits, and they are interesting in themselves. So let's recap, what happened before. So I mean, last week. So we discussed about Tori code, and there we had two kinds of generators, one corresponding to the black gates and the other corresponding to vertex, and in the NKD notation, we had 2L square physical qubits, which includes 2 logical qubits, and the distance was L. And yeah, we had let's say if you have an error, so the error is detected by stabilizers, which corresponds to measurements at the end. And if you apply a correction operator, which together with your error forms a loop, trivial loop, then you correct your error. So that's what we discussed last time. I mean, all of these ideas, they will become much more rigorous, when we understand topology, and later in the language of topology, in the fourth session, we will understand what is a stabilizer, what is a what is an error, and all these things will become clear. How can you understand logical operator from the perspective of topology and everything? So what is a logical qubit, and what do we mean by logical subspace and everything? And then we discussed about this notion of Tori code Hamiltonian, which was like made up of all these plaquettes and vertices, and it's interesting in itself. And and it's used to understand jet to spin liquids, and yeah, you can all of these ideas, almost all of these ideas, or like everything is attributed to Alex Kitaev. Yeah, so that's nice. So let's now look at a few motivating examples, like why should be interested in topology and all. So let's look at some of the like objects that we see around. So this is what is we call a vertex. This is so it's a cube, and this is a vertex, this is an edge, and this is a face. And if you can see here that if you count number of vertices, it's total, how many vertices you have? Like 8 vertices. The number of edge that if you count here, so edge here will be so number of vertices is 8, number of edges is basically 12, and number of faces in the cube is 6. And if you count like v minus e plus f, if you do this, basically that will be 14 minus 2, that is 2. And if you do the same trick, you play the same trick with a tetrahedron, you will get 2. You play it with octahedron, you get a 2. Dodecahedron, you get a 2. Icosahedron, whatever, icosahedron, you get a 2. So in fact, every convex polyhedral object, it satisfies this equation. So this is profound. You see that you can look at any such object and you can count it, and it's always 2. Like why it's 2? So this is interesting. And so this number, vertex minus edge plus faces, it's called Euler characteristic. And you can generalize it for in general, Euler characteristic is given as like b0 minus b1 plus b3 and so on, where this bn is called nth Betti number. What is nth Betti number? I haven't defined. So using homology and cohomology, I will define what is nth Betti number. And if you look at this paper by Seth Lloyd and Silvano and Paolo Gianardi, there is this Betti number that people are interested in calculating. So we will understand what is this Betti number and how it's related to homology and cohomology. And that you saw that there have been many papers last year on topological data analysis. And in topological data analysis, one of the objects that people are interested in calculating is this Betti number. And this Betti number is basically related to Euler characteristic, which which is basically whose value is 2 for the case of these simple objects. So this is motivation number 1, why you should be interested in topology. Yeah, and we will understand what is a Betti number. Another example is this is the I think the bridges of Königsberg problem, like very old problem. And the problem is that you have this river, and in the city, and there are these 1, 2, 3, 4, 5, 6, 7 bridges. And there was this question that is it possible to find a path that would traverse each bridge, passes through each bridge exactly once? And for a long time, this problem remained open. Later, Euler basically said, no, cannot, it's not possible. And the way he got the answer is that he looked at this thing, he abstracted it as a graph problem. Wherever, so all the different parts of the city, they are like nodes. So you have a node here, you have a node here, here. So basically you have 4 different locations, and corresponding to that you have 4 edge vertices here, and then whichever is connected, you connect them via different bridges. So, the edges are like bridges. And then he proved that such a walk is possible if a maximum of 2 vertices of the graph is of odd degree. But you see that all four, like, there are three vertices, like which are of odd degree. So here the degree is 3, like, I mean, if you see here, sorry, what here, you see that, like here the degree is 1, 2, 3, here the degree is also 1, 2, 3, here the degree is also 1, 2, 3, and here the degree is 1, 2, 3, 4, 5. So basically, maximum of 2 vertices should be of the odd degree in a graph. Then only such a walk is possible. And as you see that this condition is not satisfied here, so such a walk is not possible. So he abstracted the idea where he was not interested in, like how the bridges are aligned and everything. And you see that this is such a, like when, I mean, there was this problem which was open for a long time, and then by understanding the connectivity and all, like he managed to solve it. So this was Euler, like for the Euler, and we know Euler for multiple contributions. Yeah. And this is the final example that people, like ask you. They say that, like for a topologist, like coffee mug, like and a donut, like they are basically the same objects. Yeah. So what does it mean? So we will understand all these concepts today. Yeah. So that completes the motivating examples part. Let's look at, like some notion of basic topology. Yeah. So to understand that, like first we understand the notion of topological equivalence. So what do we mean by, like coffee mug and, this, yeah, obviously, like, these concepts are defined much more rigorously. And one has to start with, the notion of topological space and everything. But I mean, since we have 1 hour and like, we have to cover a lot of content and enough content so that, we could understand, yeah, like their application for quantum error correction, I think we cannot be, like too rigorous here. So we have, like the way 2 objects, say coffee mug, and, like they're considered to be equivalence is via this notion of, like homeomorphism. So what is a homeomorphism? So it's a continuous function between 2 objects or topological spaces, like you can just ignore this word, like no need to think of it here. Objects which is continuous is a bijection, which means, like 1, 1 on 2, and has a continuous inverse function. So you can, like there is a point, like in for one object and the point in the other object. And, like there is a mapping, like a continuous mapping. And you can, the inverse is also like continuous. So you have, like bi-continuous, like, in both directions. Yeah, like it's continuous and it's 1, 1 on 2. So example could be, like examples of homeomorphism is something like, continuous stretching or bending, is like an example of homeomorphism. So for example, you have this coffee mug and this is your donut, and actually, like you can deform it and you can get from here to there. Or you can have a sphere with 3 handles, and, like from here you can get, like all these objects. So when we say 2 objects are topologically equivalent, we mean equivalent up to homeomorphism, like which means there exists a homeomorphism. This takes, like 1 object to another. If that happens, then, like 2 objects are, like topologically equivalent. Nice. So once we understand the concept of topological equivalent, the next idea, like that we need to understand is this notion of topological invariant. So invariants are basically, like as we see in physics also, like these are the quantities when you perform a transformation and, like their value does not change. So basically they are properties or numerical quantities that remain unchanged under homeomorphism, because homeomorphism is what, like defines topological equivalence. So the object which are, like in the same equivalence class, they should have, like the same number associated to them. So for example, like you could see that, like this quantity that we had here, Euler characteristic, is one such, like topological, like, invariant. So for all of them, like it's the same number, 2, 2, 2, yeah, and so on. So that's nice, very good. So Yeah. So the Euler characteristic can be generalized, so we had example is Euler characteristic, and the Euler characteristic we saw it for, these nice objects. But what about, sphere and like, torus and so on? Can you calculate Euler characteristic for that? And the idea is simple. Basically, you generalize Euler characteristic to, like for general surfaces by the process of cellulation. So cellulation is nothing but, like you try to cover. So like you have seen the soccer ball and all, right? So the soccer ball, like gets cellulated by, like pentagons and hexagons, or you could try to cellulate it by, by you can cover it by this kind of, I mean, you understand it, right? Um, the squares, like example is something like, here is a cellulation, the torus, and here is a simulation of a sphere. So you basically, so example could be something like triangulation. So like you cover it using triangles, and once you have like you cover it using a cell, n cell, you can count number of faces, edges, vertices, and apply the regular formula like F minus E plus V, and you will get the Euler characteristic for that surface. So let's look at like torus. So for the torus, as we saw before, like we had number of faces was like L square, if you remember from the last time. Number of edges, that was 2L square, and number of vertices, that was L square. So the Euler characteristic for the torus is L square minus 2L square plus L square, and is equal to 0. Now you see that Euler characteristic for a torus is 0, which is not same as the Euler characteristic for a cube, which was 2. So you can definitely not, like convert a cube to a torus. And the idea, I mean, you can at an intuitive level, you can see that, like why you cannot do it. I mean, later I will explain why you cannot do it, like more rigorously. Because a torus has got a hole, and your square, I mean, the cube does not have a hole. So those objects, like they had Euler characteristic 2. On the other hand, for torus, it's 2. For a sphere, you can try to calculate the Euler characteristic. So you can triangulate it, and you can see that the number of vertices that we have here, on our is basically 1, 2, 3, 4, 5, 6. Number of edges that we have is basically 12, and number of faces that we have here is 1, 2, 3, 4, and 1, 2, 3, 4, 8. And if you do this thing, you will basically go get 2. So you can see that like sphere has the same Euler characteristic as cube, which is also expected, right? I mean, I give you a sphere, and you can you can do stretching and all this thing continuously, and you can make it as a cube. So sphere and cube, they basically belong to the same equivalence class. On the other hand, torus belongs to a different equivalence class. So I think now maybe it should be clear to you. Yeah. So the formal term which is used to count number of handles in a surface is called genus. So for example, a sphere has genus 0. It does not have like any handle, any hole. Yeah, you can see here a torus. For torus, it's 1. And if you have a sphere with n handles, that has like genus n. So it has yeah. So this is when we talk about genus, like this is the word, like I mean, we will basically mean like we are counting number of handles, like which is there. Yeah. So you can yeah, like there is some notion of orientability, not really relevant, like even if you don't understand it, like it's it won't hurt. But you can think about like a sphere is an orientable surface. On the other hand, the Mobius strip like is non-orientable. So basically you can try to assign to every cell, when let's say you triangulate a surface, you can try to assign certain direction. And if you can like if you can assign directions consistently, then you can call it a orientable surface. On the other hand, if you cannot do it, then it's a non-orientable surface. So basically a triangulable surface is orientable if we can assign an orientation to every cell in the triangulation, whatever, such that the orientation of edges of adjacent cells basically agree. Anyway, like not very relevant, but the idea is that Euler characteristic of any compact closed and bounded, orientable surface of genus G is 2 minus 2G. So this is the very important thing, that like the Euler characteristic that we had is 2 minus 2G. So it captures how many, so G captures how many holes you have. Now for a sphere, like there is 0 hole, and you can see that like 2 minus 2 times 0, that's basically 2 minus 0 equal to 2. So for a sphere we had like the Euler characteristic as 2. On the other hand, for torus, like we had G equal to 1. So if you calculate for torus the value of chi, it's 2 minus 2 times 1, and that is 2 minus 2 equal to 0. So you can see that like for torus our chi was like 0. So you can see how it captures this notion of genus, like the how many holes it has. Yeah. So there was a nice theorem by Klein in 1882 that all compact surfaces with genus G are homeomorphic to a sphere with G handle. So a sphere with G handle, like basically you can modify. So the way you can think of, like a coffee mug is like it's a sphere with one handle. And also the donut is also a sphere with one handle. Like you can think of it other part. I mean, there is one handle, right? So you can transform one to another, and so that was like some nice thing. Now let's apply this this concept to Tori code that we studied last time. Like, I mean, how it can be like useful there. So in the case of Tori code, the number of independent placate. So we had like these 3 object. Like for the Tori code, like we had faces, like edges, and whatever vertices, and the number of qubits was basically number of qubits was in the case of Tori code, that was like 2 times like it was for every edge, right? So so it's equal to E, and a number of independent stabilizers was basically like number of faces minus 1 plus number of vertices minus 1. That was F plus V minus 2. And if you count this quantity for the Tori code, like this is basically nothing but, and we know that and the number of encoded logical operator for the qubit for the Tori code is nothing but it's nothing but E, like total number of qubits, E plus n E minus F plus V minus 2. So like total number of qubits minus total number of independent stabilizers. And when you do that, you get 2 minus E minus F, 2 plus E minus F minus V. And this object is nothing but like 2 minus chi, because chi was like F plus V minus E, right? So you see that the number of encoded logical like encoded qubits in the case of Tori code, well, like you can see it as like 2 times 2 minus the Euler characteristic of the torus. So like since I did it, like let me do it again, like maybe for some people. So the number of qubits that we had in the case of torus was like basically E, and number of stabilizers, those corresponding to faces, placates, and number of vertices was F minus 1 and V minus 1. And why this one here? Because if you multiply all the placates or all the like vertex operator, you get identity. So you have one constraint for the vertex operator case and one constraint for the placate operator case, and that's why you have F minus 1 and V minus 1. So you have F plus V minus 2. And we had this relation before that, like N equal to M plus K, where K is a number of logical qubits, N is physical qubit, and M is stabilizers. So we had K equal to N minus M. So we have, so the E basically is N, sorry, N here, and F plus B minus 2 is nothing but M. And that should be equal to K. So K is 2 plus E minus F minus V, which is 2 minus chi. So this is nice because we see that the number of encoded qubits is 2 minus chi. So we looked at like very special case where our chi was equal to 0. So this kind of torus. So for this kind of torus, like chi was 0. So number of encoded logical qubits, is basically 2 minus 0 equal to 2. But now you can, instead of looking at one torus, you can look at, like torus with G handles. And for that, since we know that, like chi for a torus with G handle is 2 minus 2Z, number of encoded qubit will be 2 minus 2 minus 2Z, that is equal to 2Z, which is a very systematic way to increase number of, like encoded logical qubits, I mean. So the idea is very simple, you generalize this, like a Tori code for a G torus by cellulating a general torus with a square lattice, and you can analogously, like you can define the stabilizer generators and so on, and you can get, you can increase, you can encode more logical qubits. So you see that the number of encoded qubits that we have, or the number of logical qubits, when both are same, encoded qubits that we have, it's basically a number which depends on the surface. It's a topological quantity. So how many holes you have, that determines, like how many encoded qubits you have, because number of encoded qubits is 2 times number of holes. We have, like when we have a simple torus, the number of hole is 1, so it can encode 1 qubit. Sorry, 2 times 1 qubit. So that's 2. On the other hand, if you have 2 holes, then the number of encoded qubit that you will have is 2 times 2 equal to 4. So this is a very systematic procedure through which, like we can encode more and more logical qubits. So you see that just such a basic application of topology helped us understand, like how to generalize the Tori code. Like, we did not use any fancy mathematics. So far we covered, 3 motivating examples and, like basic topology, and that already covered things. I think today's discussion will be a bit longer because, we are discussing several things today. And so, like be prepared. Yeah. Anyway, so we discuss all these things. So let's now, like look at some more nuanced notions, and this will be very useful. Like, using this, we will understand what is a Betti number and how the Betti number is, how the Betti number can be used to calculate a number of holes. Yeah. So homology is the mathematical field which abstracts and generalizes the notion of a boundary. So what is a boundary? This is something, like we can try to understand here. So our focus, like here will be concrete aspect of homology relevant to qubit topological codes, which means, like we will be interested in, like Z2 homology, or which is, like the simplest form of homology. And here we will be looking at, like a square lattice cellulation. Normally it does not matter like how you cellulate, but squares are nice because, as we saw last time, squares are, like square lattices are self-dual. So it's better to look at something which is simple, and then later you can make things complicated and all, but it does not matter much. So let's recall Tori code from last time. So in the case of Tori code, the square lattice, we have a square lattice with periodic boundary condition. This lattice is an example of a cellulation of a torus. So you have a torus and basically you are cellulating it, like and there are 0-dimensional objects there, which are the vertices, 1-dimensional object, which are the edges, and the 2-dimensional objects, which are the placates. So let's look at, like we will call n cell an n-dimensional object in a cellulation. So 0 cell is basically a vertex. We have 1 cell is the edge, 2 cell is basically the placate. So using these notions, we will assign a notion of something called chain. I mean, this chain will be very useful. So what is a one chain? So one chain is nothing but assignment of elements of Z2 to every one-dimensional object on the lattice. This sounds very complicated, but this is very simple. You have a bunch of, like edges here. You just assign 1 and 0 to them. And you can assign different ways you could assign 1 and 0. So like, you could, so basically what 1 means that, like I include that edge. When I assign 0, basically I, like I do not include that edge. And a chain is nothing but an assignment of 1 and 0 to the different edges that I have. Yeah, so that's nice. Like this is an example of a one chain. And with one chains, you can do nice mathematics. So let's say you have one chain where you assign, like this is one example of one chain, this is another one chain. If you add them together, addition basically follows the same rule as Z2. So for example, you have 0 here, 0 plus 0 will be 0. Here there is 1 and here there is 0. So 1 plus 0 will be 1. On the other hand, here you have 1 and yeah, like I mean, so let's find, yeah, here you have 1, here you have 1. When you add them, you get 1 plus 1, 0. So basically you have, like different one chains. It's nothing but assignment of 1 and 0 to your lattice, like, edges. And it forms basically a group, like and the group composition is nothing but edge-wise, like addition modulo 2. And you have associativity, identity operator. The inverse operator is nothing but just the same, like chain, because every one chain is self-inverse. Like you take a one chain and you add the same chain to itself, because 1 plus 1 is 0, 0 plus 0 is 0. So when you add them together, you will get 0. So it forms a group, like, so it's nice, like we get this group, like formed by different one chains. And it's a abelian group. You can A plus B is same as B plus A. So number of, like elements in the group is 2 times number of edges, and that's the size of the group. So one way to think of, like one chain is that I'm interested in certain edges. So like wherever there is one here, like here, I'm interested in those. Yeah. So you can see that if I'm interested in certain edges, like, and I forget others, basically I get the figure here. So it's nothing but, like a subset of edges. That's what one chain is. I mean, like, it's nothing complicated. You just assign 1 and 0, and 1 means I'm interested in those edges, 0 means I'm not interested there. Similarly, you can think of 0 chain, 2 chain, n chain. So one chain assigns 1 and 0 to different edges, like, basically one cells. So one cell is edge. So one chain assigns 1 and 0 to one cells. 0 chain will assign 1 and 0 to, like 0 cells, which are, like vertices. So 0-dimensional objects. So we will try to assign 0, 1 to vertices. So that will be example of a 0 chain. A 2 chain basically will try to assign, like 1 and 0. So this is an example of a 2 chain. You try to assign 1 and 0 to different 2-dimensional objects, which are, like this placates. And I mean, like here, for the case of torus, like we have only 0 chain, 1 chain, and 2 chain. But you can think about, like more complicated scenario. And yeah, like, but here we are only 0, 1, and 2. And that's what we will be interested in. So similarly, an n chain is nothing but assignment of element of Z2 to every n cell. So we have this group Cn, it's group of n chains. And the elements of this one n chain, like we will represent by, like this small c, like, just lowercase symbol. So you have a small c, like belonging to C1, like this is one chain. So similarly, you can have, like n chain as Cn. Yeah, I mean, so the elements of 0 chain is nothing but assignment of 0 and 1 to certain vertices. The vertices basically, 1 chain will assign to the edges, and 2 chain is assignment for the, placates. So next we come up with this nice object called boundary operator. And boundary operator, as the name suggests, gives you the boundary. So it basically takes a n chain, it acts on a n chain, and it like gives you a n minus 1 chain. So it's a mapping from, like Cn to Cn minus 1. Yeah, like you have, it's mapping from Cn to Cn minus 1. So the idea is simple, like, so let's say you have the object here, like you have a two-dimensional object, and you apply a boundary operator on it. It basically gives you whatever is the boundary of this one. So here you have one here, and like, and wherever there is nothing mentioned, it basically means there is zero everywhere else. So when you assign, like when you try to look at apply the boundary operator, it will just give you the boundary which is like this object. So you see here you get this object, which means like you assign 1 1 1 1, and everywhere it's 0. So that's the boundary. So let's look at like more complicated object here. We have applied the boundary operator on it, and this basically should give us something like something like this. Yeah, right. Yeah, and then you can assign here, which is same as like putting here something. Yeah. So or you could add here, which is, so both of them are like it's periodic, right? So you assign here or here, both are same. So you see that it's nothing but just looking at the boundary, right? I mean, you are just interested in the boundary. Yeah, like what is the boundary, and that's what gives you. Yeah, that's what gives you. I mean, that's what this boundary map gives you. Like it's a mapping from n chain to n-1 chain. And it follows this linearity property. So basically you have, like your CJ, let's say AJ CJ, you apply your boundary map to it. It's, like it's linear. So, like you can just take it inside and that's it. So one boundary map, there is a typo here. It basically, it will give you boundary of, one chain. So you have, like one chain here, like an assignment 1. So the boundary of basically a string is the element at its end. So for example, here, the boundary will give you this. Similarly, if you have you look at the boundary of this one, like you will get, so you have something like a string here, and then a string like this. So when you look at the boundary will be nothing but, element here, 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 and here. And you see that's what you get in the, like, here. So it's nothing, you just look at a string or, like whatever the chain you have, you just look at, its boundary, and that's it. So that's nice, because as you see, like, before, whenever we had an error will correspond to a chain, and the stabilizer which can detect it, we will see later, that it, it might remind you that it corresponds to, the operators which act at the boundary. So that's nice. So you have 0n, which is, like any null chain, and since, for a 0 chain, we know that since when you apply the boundary operator, a vertex does not have any, like boundary. So but we will define it as, like some null chain, like, so basically what it means that, it's assignment of 0 to all the n-1 dimensional objects. It might sound a bit complicated, so you can ignore it for the moment, but you could think of it as, let's say if you want to think of it, it's nothing but, it's the 0 object, which if you add it to any object of the same dimension, it will not change anything. Yeah, it's just being added for the sake of completeness. So we had this nice object, like, we had this, we had the chain, we had the boundary, and boundary takes us from n chain to n-1 chain. Then we have this notion of cycle. So what is a cycle? A cycle is basically an n chain which satisfies the condition here. So when you act on your cycle with, like a delta n, like n boundary map, it gives you a null chain, like all 0. So it's basically, you can think of it as a chain which does not have a boundary. That's a cycle. So for example, if you look at, like the object that you have here, if you apply the boundary map here, like you will get 1 1, so that will be again 0. So for example, any cycle that you have, like it does not have any boundary. So it can be trivial cycle like here, or it can be a non-trivial cycle, So if somebody gives you a string, so if you give you open a string, I know this is the boundary. But if you close it, what is the boundary? There is no boundary. So cycle is, it's a chain with no boundary. But your cycle can be trivial or non-trivial. So for example, your cycle can be a boundary of certain object, and in certain chain, or it may not be a boundary of certain chain. And that will be the distinction, we will see, will play a role in defining, the Betty number and so on, as we discussed before. So nice. So the cycles that we have, they form a group. You take two cycles and you add them. Basically, we know that the cycle is nothing but the kernel of your delta n operator and boundary map. And let's say if C is in the kernel and D is in the kernel, if you add them, that's also in the kernel, right? So that's also 0. So let's call the group of n cycles as Zn. So far we have two objects, group of n chains, that is Cn, group of n cycle, that is Zn. Next we come up with this notion of a boundary. So when you take a chain and you act it on by some boundary map, you get the boundary, right? So we have this. So boundary is also a chain, right? I mean, it's a lower dimensional chain. So you have an n+1 dimensional object, you act in it by a n+1 dimensional boundary map, and you get a a chain which is n dimensional object. So for example, if you look at here, you have here a 2-dimensional object, and when you act on it by a boundary map, you get basically 1-dimensional object. So this is this was a one chain, and then when you act on it by a boundary operator, you get this, the element of a 0 chain, the vertices at the end. So that's nice. So basically one can form similarly the group basically by the set of n boundaries, and that is your Bn. So this object delta n that we are interested in, the boundary map, this is what is crucial, because the Cn's that so far we had this object Cn and then Zn and Bn, and they are related to delta n. So the Cn's basically, they are the domain of your boundary operator. Zn is the kernel of your boundary operator, and Bn is the image of the boundary operator. And in these three together will determine the homology. So notice that how it will determine the homology. We have 3 groups. So notice that every n boundary is an n cycle, but not every n cycle is a boundary. For example, this is a boundary of so if you have this placket, so if you have something like this, and if you associate, or maybe I could just draw it here. Yeah. So let's say if you have this placket where you assign 1, 0 and 0, 0 everywhere, and you act on it by the boundary operator, you will get the object which is here, So this chain is a boundary, but if you look at these ones, here and here, they are not boundaries. And so your cycle can be a trivial cycle, which means it's a boundary of some higher dimensional chain, or it can be a non-trivial cycle, which means it's not a boundary. So which means every cycle, every boundary is a cycle. On the other hand, every cycle is not a boundary. And this is what one can use to define the Betty number and all that. So notice that when you take a chain and you act it by your delta n, you get a boundary. And since boundaries don't have boundary, when you act on it by next boundary operator, you get 0. So this is called the fundamental lemma of homology, and we will be using it in the later sessions quite often. It is very important. So basically, boundary of boundaries, null chain, it's 0. So this will be very important. So yeah, so far we have been talking about 3 objects, the full group of n chains, and then we have the subgroup of n cycles, and then we have the subgroup of n boundaries. And we know that, like all cycles are chains and all boundaries are basically cycles, but all cycles are not boundaries, like always. And similarly, all chains are not, uh, cycles. So you have this nice relation. And basically homology studies the properties and interplay of these three groups. So let's say, to understand, like how these three groups, like play and all, we need to define this notion of homological equivalence. So you have a particular chain, and let's say if you add a boundary to it and you get another chain, then I would say this chain and this chain, like they are homologically like equivalent, which means you add a boundary and you get the same object. And like, why am I talking about it? Because the group of boundaries that will be used to define, that will be used to partition your entire set of n chains into different equivalence classes, like using this equivalence relation. And how do we do that? That's very simple. You just form the quotient group. So you take your this Hn, you define it as like Zn, and quotient is with your Bn. So what it is, I mean, like many of you may not know quotient group. The way you can think of it as, let's say I give you all, like a set of natural, like, integers. So set of integers, is something like minus 15, minus 14, and so on, like 0, 1, 2, like 15, 16, so on. This is a very large number. But let's say you are interested in numbers, like which are multiples of 5. So number which are multiple of 5 is something like 0, 5, like minus 5, and so on, like 10, 15, and so on. Now you can use, so you have, and you know that all these L numbers which are multiple of 5 is a subset of all, like all integers that we have. But every number which is a multiple of 5 is definitely an integer, but on the other hand, every integer is not a multiple of 5. So, but you can use this multiple of 5 idea to define, like partition the set of all integers into, from the infinite set to, like finite set, like something like 5 z, 5z plus 1, 5z plus 2, 5z plus 3, and 5z plus 4. So suddenly you have, so let's call it 0 bar, 1 bar, 2 bar, 3 bar, 4 bar, 5 bar. Suddenly you have, like you are studying, this group of integers in terms of, like whether they are divisible by 5 or not. And if they have remainder 0, then it's 0 bar. If they have remainder 1, then it's 1 bar, and 2 bar, and 3 bar, and 4 bar. Yeah. So these are different equivalence classes. So you see that we are basically using this idea whether, like if let's say I have 1 and 6, like both of them will belong to the 1 bar, right? I mean, why? Because you can add, like multiple of 5 and you will get, like 6. So you can add a multiple of 5 to 1 and you get 6. So this object, like the boundary that we have, it acts like, you can think, this is what is used to partition. I mean, it's used to define the equivalence class. And once you have the notion of equivalence class, you can partition your, the big set into smaller sets and so on. So we have this this quotient group, and the Betti number is nothing but, like the rank of this homology group. That's it. So this is nothing but, like a rank of Zn minus rank of Bn. So you can look at all the n chains, all the n cycles, all the n boundaries, and by understanding them, you can, like calculate the Betti numbers. And you will later see that these cycles, boundaries, chains, they will be very important to understand, like topological codes basically. So that's nice. So for torus, we have beta 0 equal to 1. You can calculate it, beta 1 equal to 2, beta 1 equal to, beta 2 equal to 1. So you see that when you add beta 0 minus beta 1 plus beta 2, it's equal to 0. And it makes sense, like, why are we getting it like this? Because we have, like chi, we have equal to f minus e plus v, and yeah, and this is nothing but f minus e plus v is nothing but number of faces minus number of edges plus number of vertices, which is nothing but rank of C2 minus rank of C1 plus rank of C0. And you can show that, like they are related to, they are nothing but beta 0 minus beta 1 plus beta 2. Actually, I wanted to prove it during the session, but I mean, like it will take some time, but you can in fact prove that this chi is equal to beta 0 minus beta 1 plus beta 2. Yeah. And this can be generalized for general object as alternating sum of Betti numbers. So alternating sum of Betti numbers, that will give you the Euler characteristic of the surface. So that's nice. So that completes the homology part. Finally, we try to cover cohomology. Yeah. So you see that we are interested in three objects like here, the full group of n chains, the subgroup of n cycles, and the subgroup of n boundaries. And boundaries are what are used to define the equivalence class. And if you quotient your the group of cycles by the boundaries, you get the nth homology group. And later we will see that the elements of the first homology group are basically your logical operators. I mean, we will see in the next session. And you see that this beta n, the nth Betti number, is nothing but the rank of the nth homology group. So that's nice. So far, that's what we discussed. Yeah. So nice. I mean, let's now look at cohomology. So to understand cohomology, you can think of them as they are similar to the relation between there is ket and bra. So similarly, for every chain, we have this notion of co-chain. So in cohomology, basically we develop the duals for the key aspect of homology. So in homology, we are interested in boundaries, chains, boundaries, and cycles. You just add a co in front of it. So here you will be interested in co-chains, co-boundaries, and co-cycles. And we will explain what these objects are. So you have a ket, and the dual is bra. You have a chain, the dual is co-chain, and you can, you will see, what are these objects. Okay, nice. So if you look at, what are the set of bra, they are nothing but set of linear function on the vector space of kets. So basically you have, kets, you act it by a bra, it gives a complex number. So similarly, you have a chain, basically co-chain is you can think of it as a linear functional, or assignment of 1 and 0 to certain object, such that when you take the inner product, it gives you Z2. And why Z2? Because that's what we are looking at. We are looking at Z2 homology. This can look a bit, involved, but we will explain, this thing very simply. It's very easy to understand what the P tilde is. So we have C and some n chain. So P tilde will be a n co-chain. Yeah. So and their inner product should give you basically an element from Z2. So it should give you 0 or 1. So let's look at 0 co-chain. So we have we had three objects, we have a 0-dimensional object, we have 1-dimensional object, 2-dimensional object. And if you remember the Tori code, there we we were interested in object vertices, edges, and faces. And in the dual lattice, your vertex became a face, edge remained edge, and the face became face became a vertex. I mean, if you remember from the last time. So you see that so we in the dual lattice, we are basically doing nothing but looking at co-chains, actually, as you will see. So if whatever was a 2-chain here, well, you can think of that as will become 0 co-chain. I mean, yeah. So let's see. So let's look at 0 co-chains. So you have a 0 chain, which is assignment of 0, 1 to so you have certain edges certain vertices that you are interested in. 0 co-chain is assignment of a subset of certain 2-dimensional object, for example here assignment of 0, 1 to every placket in the dual lattice. And their inner product basically counts number of vertices that lie inside the dual placket. So for example, here there is just one vertex, like you take their inner product, that will give you 1. So that's how the inner product is defined. So the zero chain was basically subset of vertices, or equivalently an assignment of 0 or 1 to every vertex. If you look at its dual, the zero cochain is subset of plaquettes in the dual lattice, or equivalently an assignment of 0 or 1 to every plaquette in the dual lattice. Yeah. So one cochain, I mean, because like edges get mapped to edges, you have you see that one chain is nothing but subset of edges, or equivalently an assignment of 0 or 1 to every edge. Its dual cochain is again subset of edges in the dual lattice, and their inner product basically counts number of places where they like intersect modulo 2. Similarly here, like similar to here, number of vertices inside the plaquette modulo 2. So that's basically you have like it intersects here and here, so it's 1 plus 1 modulo 2, so that's basically 0. So that's what like define the inner product for the cochain. And similarly, you can talk about two cochains, and like you have the similar definition. So the inner product is defined similar to zero cochain case here, and you can like talk about the cochains, oh, sorry, I think the typo. So CN is basically the group of cochains. So it's typo here. It's a group of cochains that we are interested in. So you can think about like you have the object CN, like the chains, and so these are like ket. So there is CN. This is like bra. So you take when you take inner product of the element of chain with the element of a cochain, and it should give you an element of Z2, because like we are interested in Z2 homology and cohomology. So it's just a dual object. So co-boundary is again like similar to what we see in quantum mechanics, right? I mean, so let's say you have delta n, like some boundary acting on map acting on C, and you take your inner product P tilde. Basically, co-boundary map acts on cochains. So it's basically I mean, when you take your delta n plus 1 here, it's nothing but it becomes delta n tilde, like when the damage goes one down. So it's easy to see like what. So this is how. So let's say once we have defined the one bond, like in a boundary map, n boundary map, we can use this relation to define the co-boundary map. So boundary map acts on chains, co-boundary map will act on cochains. And it's similar to, like the dagger operator or something that I mean, it's similar to, let's say you are interested in psi inner product with, like U phi, you can write it like, psi U dagger, like phi. And something similar, yeah. So it's similar kind of idea, like yeah. So let's look at like a group homomorphism. It's basically nothing but a group homomorphism on the cochains. So you have your P tilde and you have C. You look at the boundary of C here. So boundary of C will be these two elements here. You take their inner product, it counts the number of vertices inside the plaquette, and that's basically 1 here. Similarly, if you look at, like delta 0 P tilde, like, if you apply this idea here, delta 0 P tilde, because it's divided by n plus 1, and here it become n. So here you have 1, so it will become 0. So delta 0 P tilde will give you just the boundary here, and you take this, inner product with the C here, like that will basically count, yeah, like 1 here, because it's counting, like, yeah, it's counting number of places this edge is intersecting the edge here. Nice. So similarly, like, you can see another example where, like you have, yeah, like delta 1 tilde P C, like, when this will give you 0, and instead of, like if you instead of delta n, if you look at delta n plus 1 C, which is, like delta 2 C inner product P tilde, that will also give you 0. So you can convince yourself, like, it's basically the co-boundary is just defined via this map, which relates. So a boundary map takes a n chain to n plus 1 chain, sorry, n plus 1 chain to n chain. A co-boundary map will basically take you, like n co-cell to like n plus 1 co-cell to n co-cell, or like n co-cell to n minus 1 co-cell or co-chain. I'm sorry, co-chain I should mention. So basically you had Cn going to Cn minus 1 via the map delta n, and you have this delta n tilde, it will take, like Cn to Cn minus 1. So this is the relation. So, and because, like, you look at, yeah, so there is this relation which somebody could say, like, why do you have, like +1 here? On the other hand, like you do not have any here. You can think of it as because if you look at your one chain and one co-chain, they are not like, similar kind of object. Like, in the case of, they are vertices, but let's see when it's a zero chain and zero co-chain. In one case, you are looking at plackets, but in the other case, you are looking at, like vertices, which are, there is mismatch of dimensionality. So that's what, like this n plus 1 and n captures here. Okay, so we have, like next you can define cohomology group. So this delta n tilde is basically the n co-boundary map. Zn is the group of co-cycles. You can define it's the kernel of Zn tilde, and Bn is the image of co-boundary, basically, like the image of delta n minus 1. So when you again you can quotient your Zn, like, your cos. So every co-cycle is a co-boundary, but every co-boundary is not a co-cycle. So you can take, like Zn, and you can quotient it with Bn, and that will, like give you the nth cohomology group. So the Betti number beta, and again you can define it as the rank of the nth cohomology group, similar to the previous case. So for Z2, the cohomology is simply homology on the dual lattice, but this does not hold generally. And like, you can look at ZD homology, and that will be, like that can be more nuanced, and it's a natural framework for QD topological codes, like if you want to understand. So let's summarize everything. I know that this has been like, much more involved, and it will get a bit involved and all, because later we will be discussing how to apply these techniques to understand Tori code and subsystem codes, and like, and like, Tori codes and all, like, in general topological codes. And so let's like summarize, like, what we discussed. So we discussed about this notion of this number called Euler characteristic, which can be number of vertices minus edges plus faces, and we know that, like it's 2 for this object, and you can cellulate a general surface, and you can calculate this number. This number can be also calculated by like alternating some of the Betti numbers. And what are the Betti numbers? We get it through homology and cohomology. And then we say that, like we have this notion of topological equivalence, which comes from, like homeomorphism, which is, like invertible map and all continuous on both sides. And two objects are topologically equivalent, like we said equivalent when, they are equivalent up to a homeomorphism. So we had the n cells. It's basically an n-dimensional object in a cellulation, 0 cell, 1 cell, 2 cell, vertices, edges, and plackets. And a 0 chain is assignment of, like assign an element of Z2 to every vertex. 2 chain assign 0 or 1 to every placket. N chain assign an element of Z2 to every n cell. So that's what 0 chain, 2 chain, n chain, or like, so on. And then we talked about this boundary operator, which, like gives you the boundary of your chain. And so we had the Cn, the full group of n chain, Zn, the subgroup of n cycles, Bn, the subgroup of n boundaries. And we have this inclusion relation that, like every boundary is a cycle and every cycle is a chain, but the other way around, like generally. And you can, like you can quotient it. So quotient basically what means, like you try to, like a quotient group is basically, like a group of coset. Like it's a bit involved to define, like you need to define 4 sets, and through that you can define the quotient group. But I had put the definition before, but you can think of, like the set of integers, and set of integers is like has infinite many elements, countably infinite, but you can be interested in, like a set of integers which are divisible by 5. And then if you take the quotient of the set of integers by, like the set of integers which are divisible by 5, you have only 5 elements in the set. So you divide your entire set of integers into equivalence classes, depending on, like in the sense that you have elements which are divisible by 5. So, like they can be written as 5z, and then the numbers which can be written as 5z plus 1, 5z plus 2, 5z plus 3, 5z plus 4. So it's nothing but, like a division of it's partition of your set into, like different equivalence classes. Yeah. So so that's how you can think of, like intuitively the quotient group. Yeah. So you see that you have an equivalence relation coming from the fact here that whether the integers are, like divisible by 5 or not. And similarly, let's say you have an integer which is, like a, another integer b. If you can add, let's say, multiple of 5 and you can get the other integer, then they will belong to the semi-equivalence class. So similarly here, let's say you have a chain, and if you can add a boundary, like you can add a boundary and you get another chain, then they will belong to the semi-equivalence class. So in this sense, you can take the set of all chains, and you can, you can take the set of all cycles, and like you can partition it using the boundaries. Yeah. And then we talk about this notion of beta. And then we had this fundamental lemma of homology, which is, like boundary of boundary is basically 0. So yeah, so you apply 2 times, that gives you 0. Then we talk about cohomology group, like similar ideas, like, you had delta n operator here you have, like similarly the n co-boundary map, and then you look at the kernel of this map, that is Zn, like image, Pn, and like and then again Zn, like this quotient group will give you the nth cohomology group. And the Betti number is the rank of the nth cohomology group. And how do you define the co-boundary map? Via this, like relation. Yeah. So that's it. I mean, we covered, like, in summary, we covered the notion of topological equivalence, then topological invariant, which was the Euler characteristic. Euler characteristic is related to Betti numbers, and it's also used to count the number of holes. It's like 2 minus 2z. We talked about how can you use it to generalize the Tori code to, like earlier Tori code had 1 hole, but you can generalize it to G torus, where you have G holes. Then we talked about the notion of like this chains, and how you can define, like the cycles and boundaries, and then how they play together, and you can use the notion of boundary to partition your set into different equivalence classes, and that gives you the nth homology group, and its rank basically gives you the Betti number, and the similar. And then we had this fundamental lemma of homology, cohomology groups, which was, like defined in terms of the n co-boundary map, and the co-boundary map is defined by this relation here, and we have this Zn, Bn, and they together they again form nth cohomology group, and then you have this rank as the Betti number. And yes, so that's it. So I think we have all the ingredients now to understand topological quantum codes, which we will understand next week. We will also look at bosonic codes and subsystem codes. So I think this concludes the tutorial for today. I think, can we maybe